afternoon, ladies and gentlemen. So we are back on the 5th oral sessions, and in these sessions we have, it should have been 5 speakers or presenters, but up to now we have 4 speakers. And the 4th will be delivered their presentation online. So before that, so let me introduce myself. So I'm Lucia Dwi Krishnawati. My name is too Indian, isn't it? With Krishnawati. Good, yeah. So I'm from Duta Wacana Christian University, from this university, from the informatics department. Yeah. Okay, so I would like to check whether the presenters are already in this room. So please apologize me if I mispronounce your name. Yeah. So the first speaker will be Su Wan Ping. Mr. Su Wan Ping, are you here? Mr. Su Wan Ping? No, not here.
It's the automatic.
Okay. And then Mr. or Miss Chai Nun Damrong Rat. He's not here yet. Oh, he was here, yeah, but he's not in this room. And then the third is Mr. Muhammad Hanan. Are you here? Okay. And Mr. Ziad Diarafi. Are you joining online? If you're joining online, so please say yes or say something. Open your mic and say something, so that we know that you already joined the room. No? Okay, so it seems from 4 presenters, there is one ready. So please allow me not to call you in order according to the schedule. So just allow me to be flexible. Yeah. So for Mr. Muhammad Hanan, you are here, please present your article or research finding. Yep. Oh yeah, so I will use the bell for the time signing. So each speaker will have 13 minutes to present their research finding, and we will have 3 minutes discussions. So when it's already 10 minutes, the bell will ring 1, okay, and 13 minutes will ring 2. It means that your presentation finished, and we start the discussions, and when the time is out, and then the bell will ring 3 times. Okay, thank you. Yeah. So now please, Mr. Muhammad Hanan will present about the application of data augmentations to reduce session variability in an I-vector-based speaker identification system. So, Mr. Hanan, time is yours.
Okay, thank you. Good afternoon, everyone. I'm Muhammad Hanan from Bandung Institute of Technology, and This is joint work with my supervisor, Dr. Desi Pujilestari. And today I'll present application of data augmentation to reduce session variability in an I-factor-based speaker identification system. That our O-COCOSDA submission, that I walk through the dataset, the I-factor pipeline, and how simple augmentation improve robustness under cross-session mismatch. Okay. Speaker recognition has evolved from early template machine to compact statistical models. A key milestone is the I-factor framework, which compress high-dimensional acoustic feature into a small picture while preserving speaker identity. And the main challenge is the session variability that change in microphone channel from acoustic or even psychology and physically, and that make two recording of the same speaker look different and reduce the accuracy. And we use I-factor because they are transparent and computer-like, which set data limited. In contrast, neural embedding often need a large corpora and heavy training. So to improve robustness, we apply the data augmentation, which is the additive noise, reverberation, gain, and speed perturbation to mimic realistic session shift. This is the problem statement and objective scope. The audio is only in Indonesian language, and the recording in simulated condition, and the system is text independent, and every audio for each have only single speaker per kit. That means that's no overlap speaker in every audio. Here how we build the voice of dataset. That on the left, you can see the flow that we first gather the original speech from the several sources, then later create augmentation and build a standardization subset. That source and count that, which is TIT-ML IDN, which have 20 speaker, LibriVox 37 speaker, ProSci-I that 14 speaker, ISR Indonesia 10 speaker, and self-collection is 11 speaker. And for self-collection, we recorded in a quiet room with an external mic at a normal speaking pace. And each speaker did 4 simulated conditions to mimic their psychology and masking while keeping identity cues, which is audio is a normal, flu, when it's flu, the condition when to have a toothache, and using the mask. And we recorded 11 speakers that each speaker have 32
Recording
long
in progress.
scripts and 12 short scripts. So from each raw audio, we create 4 time domain augmentation to mimic a real recording change while keeping identity cues. The first is additive noise for every utterance. We sample 1 muson noise file and mix to SNR 15 decibel. And the second, artificial reverberation, that we randomly pick 1 ER from small or medium room sets and convolve it. And the third is a gain that we apply a random from -5 to +5 decibel change per recording, and this model basic level of difference. And 4, that is speed perturbation, that apply a factor alpha between 0.9 and 1.1, a narrow range to avoid distortion. And we use 1 augmentation per utterance rule, so each copy represents a single condition together with the clean version. This yields 6 recording conditions per utterance. And to keep experiment clean and reproducible, we standardize file name and metadata that each file encodes speaker, session, and recording ID. And we divide data into 3 sets. The first one is training for the I-factor training component, which is had UBM, T-matrix, and backend when needed. And then the enrollment built from self-collection long script recording. And the last is testing that uses self-collection short scripts only and never augmented to to avoid a leak. And the main source dataset for training are TIT-ML IDN, LibriVox ID, ProSci-AI, and ISR Indonesia. And for the enroll or test come from our self-collection set. That's our standardization foundation before the modeling. Okay. This is the diagram shows the full pipeline from the training to the enrollment and testing. The first is feature that we first unify the audio to one format, which is mono 16-bit fixed sample rate. Then we extract 39-dimension MFCC with a 25 millisecond window and 10 millisecond overlap or hop. And we apply per utterance means subtraction and keep variance unnormalized, so later we can still observe the gain effect. And second is UBM statistic that we train 128 component diagonal JMM UBM on the training corpus, initialization by use by key means, then EM into until the convergence. And so for every recording, we accumulate Baumwoll statistic and normalized by Mr. Wade. And then the total variability matrix, those the stats fit thematic trainings, projecting the superfactor space into a 200-dimension latent space that captures speaker and the section factor, extracted by effector, are length normalized before the scoring. And the enrollment and testing from the long script recording, we built one speaker effector model per speaker, and from the short script, we extract the test effector that both use the same feature or TV dimension pipeline and length normalization like in the training. And then scoring backend that we prepare the LDA plus cosine distance discriminative projection with cosine similarity versus the PLDA. Which model between or within speaker variability and scores via log likelihood ratio length norm is applied prior to both. And then the last is evaluation that we report accuracy top one and the equal error rate. That is operating point where false acceptance equal false rejection. So the accuracy reflects the identification success, while ER summarize the verification trade-off. Okay. So this is our design experiment that the question is how much the augmentation and overlap matters for I factor. So we use 2 times for factorial for the training section. That factor number 1 is training augmentation, which is using augmentation or not using augmentation for the data training. And the factor number 2 is the train enroll overlap. That we define the 4 type, which is the non or channel overlap, which is the microphone that is overlap, the speaker overlap, and the all audio and speaker is overlap between the train session, between the train and the enrollment. So then after that, we evaluate each setting under 4 enrollment scenarios. Scenarios number 1, the normal session, which is no enrollment in augmentation. Scenario number 2 is with normal session and with enroll augmentation. Scenario number 3 is we enroll the all 4 session audio and no enroll augmentation, and scenario number 4 is all 4 session with enroll augmentation. So this is the table maps the factorial to 8 model that each row equal I factor model from experiment 1 until experiment 8. And that we also compared that experiment 1, 3, 5, and 7 to see how the overlap effect without the augmentation, and the experiment 2, 4, 6, and 8 to see them with the augmentation. That every model in there is evaluated under scenario 1 until 4, which is a different enrollment condition. So this is a slide that summarizes all the 8 models experiment 1 until 8 for both scoring methods and for augmentation placement without training only, enrollment only, and both. The first is LDA plus cosine distance, that the effect of augmentation is mixed, that training only augmentation can help when the channel match, but in other settings, accuracy can drop by 2 until 4 points. And how about the PLDA? From the result, the picture is consistently positive that the training-only augmentation gives clear gains about 22 points accuracy and with their minus 10 EAR in several settings. But in train and enroll, give the augmentation is the strongest in scenario number 4. That we often see accuracy is more than 90% and equal error rate is between 2 until 6%. And this supports the idea that LPLDA models within or between speakers variability, so it benefits more from realistic time domain perturbation. So here I focus on how overlap between training and enrollment change the outcome. With the LDA plus cosine, the base case is when the speaker overlaps, and with PLDA, performance improves as the train or enroll distribution align from none to all. It's consistently more stable across the condition. So this is ablation variance of UBM components from 128 until 512 under a controlled session number scenario number 4 settings. As the UBMs grow, both back-end and degrade, accuracy drop and EAR rise. The likely reason is model complexity, exceeding data scale, limited data, and many Gaussian are under-trained, so Baumwell stats become sparsy and noisy. And here we vary the number of enrollment utterance per speaker that with LDA plus cosine performance improves steadily as we add more utterance, but EAR drop modestly. But in PLDA, small counts are unstable. It becomes reliable around 32 utterance per speaker because within speaker conference need enough the sample. So here are the practical takeaway for robustness. PLDA with length normalized effector is the safest choice. Use the symmetric augmentation. And on this scale of data, UBM 128 and T-Maastricht 200 degree work well, and PLDA stabilize more than 32 enrollment utterance per speaker. Yeah, to wrap up, augmentation is highly effective with PLDA. We see the big accuracy gains and the lower EAR, while LDA plus cosine only benefits in overlap condition and may drop elsewhere. And yeah, I think that's all from me. Thank you for your attention.
Okay, just give us applause to Mr. Hanan. And thank you for your presentation. Is there any questions? Okay, please.
Thank you. So I have two questions. So the first one is, I'm not sure I follow what are the choices behind the reasons behind the choices of the augmentation that you use. And the second one is, I'm curious whether you have done any evaluation study regarding how much of each augmentation techniques you use contribute to the overall performance, and also whether you already also explore the more general augmentation techniques such as spectral augmentation like frequency masking or time masking. Thank you.
Sorry, can you repeat the question number one?
Yeah, so I think I saw a list of augmentation that you use for the speaker variabilities, but I'm not sure I have read what are the reasons for the augmentation techniques that you use.
Your question that why I'm using a time domain augmentation?
Yeah, exactly.
Oh. So, okay. Thank you for the question. The reason why is actually I read some paper that time domain, it's really good method to increase the first that increase the data, but also increase the accuracy for which is in general in speaker recognition. So from that paper, I used the same method of augmentation and used the same parameter that the paper suggests to that. So that's why. For the question number 2, sorry.
The second.
The ablation study, like I think there are some choices of augmentation techniques you have, and I wonder how much each of them contribute to the final accuracy.
So for the accuracy, like
Yeah, for the total accuracy. Yeah.
for the accuracy, the LDA, it's because we have to constrain that the limited data. So the accuracy for the LDA is more stable than the PLDA one. That the PLDA is the accuracy of PLDA is depend on how much the data had in the enroll section. Yeah.
Okay. So thank you, and unfortunately the time is up, and thank you very much for the presentation and discussions. So I'm really sorry that I misunderstanding because the paper was not there. So Mrs. So please, you okay, and so I would like to call the next presenter. So Mrs. Subhya Satchichandra. Oh, sorry, Mr. Subhya Satchichandra. So he will present his research entitling Accent Conversions Preserving Speaker Identity in Native English Synthesis. Okay, so please, time is yours.
Yes. Madam, this one will be the next slide and this one will be the previous slide. This one next slide and this one the previous slide. Oh, thank you. Oh, thank you. Good afternoon all. Myself Shobbosati Chandra. My manuscript title is Action Conversion, Preserving Speaker Identity in Native English and Synthesis. I want to thank all my co-authors, Ms. Pooja Bharti, Devlina Pramanik, Samal Kumar Das Mandal, and Dr. Riya Sil Madam. First of all, I want to say what is action conversion. Action conversion is a speech processing techniques that modify speaker accent or pronunciation style whilst keeping their original voice identity keeping unchanged. During the time of action conversion, basically we face few challenges. First one is the speaker identity. This is a very big challenge when we work in action conversion techniques, and another is the data limitations. When we work with the low resource languages, data is very few amount of data with the transcript and the annotations are available. So it's a big challenge for us. Next slide, I want to demonstrate a process. That means what is basically action conversion. In this slide, I want to describe that one Japanese speaker is teaching chemistry. He is a very good lecturer. There is 3 category students are there, learner. First one is the Japanese student whose native accent is Japanese, and second one is the American student, that means native accent is American English. And in third category, we want to use the action conversion technique. That means the Japanese speaker speech will directly go to the action conversion module, and from the action conversion module, the accent converted English will be go to the student. And here we can see the facial expression of the three category student is that the first Japanese student is very happy because he is understanding the everything because it's quite similar to his own accent. But the American student is not quite happy because he is not getting the proper accent, so the intelligibility will be low. And in the third case, we can see that the student is happy here also because he is getting his own accented English from the action converted module. So this is nothing but just a demonstration of why, how we can, how the action conversion technique will basically help to this kind of work. Next, our proposed approach. In our proposed approach, first we use the embedding extraction. We use the speaker and accent embeddings that we will extract from the source audio. Then we will extract the same speaker and accent embeddings from the target speaker. And third is the speech recognition techniques we use here. This source audio will go to the ASR and it obtains the text transcription. And here we use the transcription and the speaker and target speaker embeddings for the synthesis. Now speech generation part, it will combine the three things, that means the transcript and the target speaker embeddings and the target and the speaker identity embeddings to generate the speech. In vocoder synthesis part, we convert the male spectrogram to the final speech signal. Here we use the normal neural vocoder to generate the target accent. Here we can, you can see the architecture of the speaker and accent encoder, both type of things. The architecture is basically based on the ResNet 34 architecture, which contains 16 residual blocks, and encoder which we use here identifies the speaker identity, while accent encoder captures accent and prosodic features using a shared CNN architecture. And the speaker encoder is basically trained with the G2E loss to ensure high similarity for the same speaker and strong separation across different speakers, enhancing distinct identity representations. In our training part, we basically use the Libri speech dataset. This is openly available for our training data, and VoxCeleb 1 and VoxCeleb 2, this is also openly available, and the VCTK corpus for the training part. And for the training, speaker encoder training, we use the, we basically use 100 epochs using Adam optimizer, and a stepwise learning rate, we use here learning rate is 0.001, and model optimization to yield high intra-speaker similarity and inter-speaker distinction. In action encoder training, the similar protocol we followed, the 100 epochs, but in this case we use cross entropy loss. The reason is that the action class is already predefined to enhance the action recognition and replication accuracy. Here, Here we can see the graphical plotting of the variation of the training and validation loss of the speaker encoder for the 100 epochs in the first picture, and in the second picture we can see the accent encoder, the variation of training and validation loss for the 100 epochs. Here we can see that for the action encoder, almost the training loss is reducing, but in case of the speaker encoder part is almost saturated after 40 epochs. So first we have done the speaker in action encoder part. So in both cases we use the 100 epochs in this case. Here we have visualized two types of speaker embeddings. The first UMAP visualization we use for the speaker embeddings of test speaker for the VCTK corpus, and this is not quite clearly visible. And but in the second case, that is TSNE visualization techniques, we use the VCTK corpus for the speaker embeddings. We can clearly see that the clustering part of the different speaker here. Here we compared the word error rate for the different action ASR models, that is deep speech, whisper, Hubert, and web to vector. Here we can see that we are basically choose the lowest word error rate, that is we obtained for the whisper model. That's why we use whisper for our primary speech encoder. And in our second comparison, we use the TTS model, where we use MCD and PESQ score for speech similarity and quality, free VC24 out from other multilingual TTS models, effectively preserving speech, timbre, and intonation for natural sounding speech. We have done two types of evaluation. One is subjective evaluation and another is objective evaluation. In subjective evaluation, we have done three types of assessment. One is accentedness test, and another is the naturalness test, and third one is the speaker similarity test. In this case also, we can see that the result is in our TTS, it's achieved quite good result here. And in speaker similarity test, this is also quite clear that our TTS is performing well in these cases also. In objective evaluation, in this case, the free VC24 module is performing well than our TTS, is almost score 0.78 similarity. Here we use cosine similarity matrix for objective evaluation part. Here the thing is high value, that means the closer match to the target speaker. So in this case, voice free VC24 model is performing well than our model here. In conclusion and discussion, I can say that this work presents an action conversion system that changes non-native English speech into native English by using speaker and action encoder with an ASR and TTS model. The system improves speech clarity, naturalness, and intelligibility, showing the key role of speaker and accent embeddings in high-quality speech generation. I want to acknowledge the AI for CPS lab of IIT Kharagpur for this work. And here are the reference related to my work. Thank you.
Thank you very much. So just give applause to Mr. Chandra. Yeah, okay, we still have enough time to have a discussion. So first, I would like to ask the audience whether you have questions for Mr. Chandra. No? Okay. So if not yet, I hope you still thinking about that. Yeah, maybe later. So just let me pose you questions. So do you plan to embed this or your work into a broader application?
Sorry, madam.
Embed. So you have the speaker.
Speaker embeddings.
No. This is
Speaker preserving.
accent conversions.
Action conversion,
Okay.
yes.
Yeah, your system. If it's stand alone, I think it will not be so useful. I mean, it should be more useful if you embed this accent conversions to a broader system. Now, do you plan to do that?
Yes, definitely. We are basically applying this for the Indian accented English and the American accented English, and also for the British accented English. Now we are also working with some Japanese professor also, because they are also face the same kind of issue. So if real-time action conversion is possible, then it will be very helpful those who are traveling for tourism purpose or for education purpose. So if we have a specific device, just like our specs, so if that device will be trained in my own accent, so it will be very easy for, so suppose if I am telling, someone may not be comfortable with my English, because the accent related issue will be there. If that device will be trained in his or her own accent, so my speech will directly convert it to his or her accent, so it will be very easy for her. So what I am basically telling.
Yes, right.
So this is the main motto of this thing, but it's very, we are working on because the data set is a very big issue. So we need the huge amount of data set and the regional languages data set we required. So we are working on that. Basically, initially we are working with the English, because English data set is largely available. So we are working on that.
Okay, right. So my question is based on what I think. If it is embedded to a meeting platform like Zoom, for example, so I think it will be very beneficial.
Definitely,
for,
definitely.
those who have difficulties in understanding.
Surely, if that device will be available in online Zoom, on Google Meet meeting also, so it will be very easy for both the listener and all the speaker, because the conversion can be vice versa also. If you use the cycle can architecture, then the conversion will be vice versa. So it will be beneficial for the speaker and the listener also, in both cases.
Okay, thank you very much. And I think the time is up. So let's once again give applause to Mr. Chandra. Thank you. And I would like to know whether other speakers are already here. Mr. Su Wan Ping, are you here?
Yes, I am.
No.
I'm online,
Mr. Chai Nun Damrong Rat? Yeah, okay, so please. So Mr. Chai Nun Damrong Rat will present his research on Thai MRC, a comprehensive corpus for advancing machine reading comprehension in Thai. So time is yours.
Thank you very much. My name is Chai Anand Damlongrat from Thailand, NASDA Thailand. Today the topic is about the Thai MRC. This topic is a bit cheap from the speech and audio, but because this is mainly for the text orientation. The MRC is machine reading comprehension. Actually, it's kind of the QA question corpus that we give the context and let the AI to read the context, and we can ask them. Before this, let me share you about what is the journey of Thai LLM. Yes. Excuse me. Uh, if we remember, ChatGPT is released on the late 2022, right? In the early of 2023, Thai community already formed up to create our own GPT, like a ChatGPT. We call Open Thai GPT. And then in the middle of the 2023, we released our very first model. It's a beta model. And then 1 year later, in the April of the 2023, we released the version 1.0. At that time, we released our LLM based on Llama 2. And then 1 year later, when the technology is has many updated, our organization named Nectex also have the release foundation model called Open Thai LLM, and our fine-tune called Patuma LLM. And for the organized community also released its own model. It's called Open Thai GPT version 1.5. At that time, we both community use the best model is Shenbon 2.5. And then now until the very soon in the early of next year, we will release Thai LLM. Is a collaboration of many organizations in both public and private sector. In the early of the next year, we will release a small, middle, and large model. And because of we creating our own Thai LLM, then we found a problem. We found a challenge that because AI using the data as its food, right? And we found that we have the problem that is lack of corpus of Thailand, our language. Because Thai is like only country that use Thai, then the corpus that existing corpus is very small and not variety. What does this mean? If we see in the common crawl, this is the community that collect the information from the website over the world and every languages. We can see that the most proportion is English, is almost 45%. But Thai language is in the order of 21st, is less than 1%. It's only 0.3 almost. Then it means in ChatGPT, Gemini, and Claude or everything that they probably should use this corpus. Our language is very small portion. Then what's next? For the common crawl, we can use for the pre-training, right? But for the fine-tuning, we also check for the Hugging Face. This is a community that people share models and data set. If we search for Thai, comparing to the English, it has a big gap. Then it means our language is very lack. And not talking about the duplication as well. Another issue is the existing corpus is translated and maybe use AI to generate. And the problem is because the AI or LLM, because Thai corpus is very, very small, right? Then when the AI generate the incorrect grammar, then it is another issue. Then we propose how to create our own man-made corpus for Thai language. And we focus on various tasks as well. The key concern is about the criteria for creating the corpus is the correctness, variety, and natural language. Let me see the overview. Based on our project, we try to release the corpus that firstly generate from the general annotator like common people in the big data set like 120K. And another one is a smaller one, but we focus on creating by the linguistic people and focus on why and how, because why and how is more difficult than factoid. Factoid is mean like raw data, like a number, date, name, or who, something like that. And in this paper, we focus on the machine reading comprehension, that as I said before, we put the context to let the AI to lead, and we use it answer question answering. Based on our purpose, we create our methodology that, like I said, we concern on 3 criteria: correctness, variety, and natural. For the correctness, we use the annotator have to put the reference and has a human in the loop, and natural as well, human in the loop. For the variety each criteria, this is what we focus, because based on our experience, when we made the corpus, people just make a pattern, like change some entity, and then they have many records, but low quality. Then for the variety, we focus on various domain and question complexity that I will talk about it later. Formality is like a formal, informal. Question type, WH question, yes, no, and how and why, something like that. And we also, even we said man-made, but because the number is huge, then we need some tools, and we use AI as a tool. And for make the answering, we have a guideline that the annotator have to read the context and extract the answer from that appear in the context, and then rewrite the abstractive answer later. And for the labeling of the data variation, like question complex, we use the DIKW level. DIKW is the key. It is a data, information, knowledge, and wisdom level that I will show it later. And question type, we need variety, like a factoid, when, who, what, something like that. And explanatory is a why and how, and binary is yes, no. And formality, formal, informal. Based on because this is focused on the MRC, the machine reading like a QA, then how the people make, the annotator make the corpus, they have to read the corpus, extract the answer, and then rewrite the answer again to make the naturally, and based on the criteria that formal, informal as well. And for the DIKW pyramid, this one is to label the corpus, these records. The question is belong to which level. For example, if it means that data is like to the question and answer is related to the direct number, like how many budget for this year, something like that. But for the higher level, it need the knowledge. It need the linkage of the idea. For the data is a lot, like a raw data, raw fact. For the information, it's like to grouping the data together, and then we really use it more useful. For the knowledge, it means they have to link the information together to understand why it's happened. But for the wisdom, it's like to be able to project, to predict what will happen. These 4 levels of the question that we would like to make. And after that, when we have the question, answer, and we have the many labeling, right? The DIKW. When we use the LLM as a judge, like we use 3 LLM to judge the, for example, DIKW. This sentence is the knowledge level or not. We use 3 LLM to vote. If they have a consensus or have a majority, then we believe the model. But if the sound, there are no consensus, then human will be in the loop. And we will use the judgment from the human as the core labeling. This is the core idea. And the result is, this is the sum of one record that there are many columns. And this is not all of them, but you can see in the middle this has a dot. That is mean there are many columns that we label. And based on this result, we already boot up the quality of the question. Then it means we boost the IKW. We try to focus on knowledge and wisdom level because in the past, many of corpus has data and information level. Then that is why we focus to make this kind of level. And knowledge is almost 58%. This is what we achieve. And when the AI has no consensus and the human have to be in the loop, this is the character of each model. You can see three model we use, ChatGPT 4o mini and ChatGPT o3 mini and Gemini Flash 2.0. This is the top tier model at that time. And you can see the 4o is similar to human judge on the basic level. But Gemini is similar to the human judge on the knowledge. And O3 is good for the wisdom. This is the result that we can find. And we use this corpus in the, we held the hackathon in the middle of this year. And we use this corpus, some of them in the QA track. And the result, the winner used this corpus to fine-tune its model, and it's competitive, and it wins for the baseline model. And thank you.
Okay, just give applause to Mr. Don Rongrat. Okay, good. So we continue to a discussion session. Is there any questions? Oh, okay, please.
Yes.
Test speaker.
Hello, am I audible? Yeah.
Okay.
Thank you for your presentation, sir. You mentioned that this corpus is used for question answering, like basically how large language model, and I also noticed that there was a slide you said extracting the answer and then abstract. So could you please explain how, because since for low resource languages like Thai and similar languages, extracting the basic words and then getting the abstract answer, that again depends on the language generation, right?
Oh no, by human.
By human.
Yes.
So can you please explain the...
We design like this because we want to prevent how the annotator use their own knowledge to answer that not related to the context. Then the first step, the annotator have to delete the question and then define where is the answer that appear in the context, and this is the extract answer. The annotator have to highlight, and then we will know the position of the answer, right? Based on this extracted answer, then the annotator have to it's like a rephrase to create their own wording based on the formal, informal, semi-formal, like a formality level in the abstractive answer. Then we can use, if we use like a traditional ML, like an answer, then we can use the extract answer. But if we want to train for the LLM, generative AI, then we can use the abstractive.
Thank you.
Okay. Any other questions? No? Okay, we still have time. So if I notice your presentations, so you have like 120,000 annotated data, is that right?
Yes.
Okay. So how was it done? Was it through crowdsourcing? because you said that it was done by human and annotate 120,000 data is quite a challenge. Yeah.
Yes, thank you for this question. Is very complex, but in short, the organizer that take this job, the company have allowed 20 to 30 people to hold the project, but based on this QA MRC. But our own originally design, we would like to let the actual crowdsourcing, not only 10 people, but
Okay, so
based
many
on the
people.
policy
Yeah.
of the government section, we to pay the big budget. It has a process. Then the different type of the company can take, but there is a professional.
Okay, I see. Yeah. Okay, thank you very much.
Thank you very much.
So, because time is up, so just please join me again to give a big applause. Yeah. Okay, once again, I would like to ask Mr. Wan Ping Su and Mr. Ziadia Rafi, are you already joining the Zoom meeting?
Yes, I'm
I'm here.
online.
Hello?
I'm Wan Ping Xu. Hi. Okay. Yes, I'm here.
Oh, okay. So sorry for the false gender. Yeah. Okay. So Miss Wan Ping Su will present about automatic classification of dyslexic tone sandhi in Wuhan dialect based on functional principle component analysis. Okay, so time is yours.
Okay. Thanks for the introduction. Good afternoon, everyone. I'm Xu Wanping or Wanping Xu from China. It's a truly honor to have this opportunity to share our research here. The title of our presentation is Automatic Classification of Dyssyllabic Tone Sandhi in Wuhan dialect, based on functional principle component analysis. While this paper is categorized under the technology track, its core focus lies more in linguistics than industry. So my presentation will be structured into three main parts. First, let's see the linguistic background and the research problem. Tone Sandhi refers to the phenomena where citation tones change when individual syllables are connected in speech. Like in Mandarin, the characters Lao and Hu both carry the tone 3 in isolation, but in the dysyllabic word Laohu, tiger, the first syllable sounds like a tone 2. However, tone sandhi rules are far more complex than this. In many other Chinese dialects, they cannot always be predicted merely by the combination of individual tones. Take the Tang-Siku dialect as an example. Different grammatical structures lead to distinct tone sandhi patterns. For example, an AN phrase like Gaoshan, high mountain, and a VO structure, Shaotang, cook soup. They both consist of 2 tone 1 syllables, but their actual pronunciations follows different tone sandhi patterns. Such variations in tone sandhi are shaped by a variety of factors, including individual differences like speakers' habits, and the differences between words themselves, actually. So manual labeling of each utterance is necessary, which is not only time-consuming, but also prone to subjectivity. Therefore, we aim to develop an automated method to classify tone sandhi patterns in Chinese dialects. So our study uses data from the Wuhan dialect. It's a variety of southwestern Mandarin of Chinese. Similar to Wu dialects, Tongxuandi in Wuhan dialect is affected by grammatical and semantic and or the other factors. There are two main patterns decided by the position of stress, like the one is left stress, with stress placed on the first syllable, and the right stress with stress on the second one. And what is particularly noteworthy is that the tonal distinctions between these two patterns are extremely subtle. You will see that later. And moreover, beyond the pitch, tonal duration also serves as a crucial factor in the distinction of Tongxuandi patterns. For these reasons, the Wuhan dialect Tongxuandi patterns provide an ideal test bed for automated classification methods. So let's move to the second part. As shown in the figure on the right, the citation tone system of the Wuhan dialect has 4 tones, and they are high, low, falling, and rising. It's a very simple system. And so our research uses a data set with 16 tonal combinations covering all kinds of compounds and simple word structures. And there are 30 native speakers join the data collection. After taking out all the wrong recordings, we ended up with 80,130 valid syllabic tokens for our follow-up analysis. And since pitch contours and our functional data, which is complex themselves, and plus there is duration information, makes it a multidimensional situation. Our first step is to reduce the dimensionality of the raw data. But a key challenge here is handling intersyllabic relationships, since Chinese is a tonal language, so pitch contours are constrained lying lexical tones. When the pitch target of adjacent syllables differ significantly, there will be a large gap at the boundary, as shown in the right picture. And if we try to fit the raw pitch data into a single continuous curve, it distorts both syllables, like the blue lines shown in the picture. But on the other hand, Tongxuandi in connected speech is really a holistic progress. The tones don't change in isolation. They work together as a part of a larger system. So in our analysis, we need to keep those interactions instead of treating each part separately. To do this, we used functional principal component analysis. In simple terms, this method describes each pitch curve with a mean shape plus several main patterns of variation. Also, it enables us to examine joint variations across multiple dimensions, such as pitch and duration in our case, while maintaining their relative independence. And another thing is, usually, joint analysis of FPCA is used for simultaneous dimensions, such as pitch and formants measured over the same time range. But since FPCA is based on covariance, it doesn't. That means we can extend it to study covariance across different syllables within the same word or phrase. In our task, we use functional PCA to examine how the tonal shapes of the first and the second syllables co-vary, and we also include the tonal duration ratio as a third dimension. The resulting principal component end up capturing the interactions between tonal k-means clustering, which is an unsupervised one, and mixed effects logistic regression, which is the supervised one. And for real-world use, we trained the k-means on all 8,000 unlabeled tokens mentioned before. And among these, 2,000 tokens were labeled with sandy patterns by native speakers, and then slaved into training and test set at an 80-20 ratio. The logistic regression model was trained on the training set, and we on the test set later. So let's see the results. First, this is the principal component we get from FPCA. The PC1 as the right thing shows. The first principal component explains the largest variance when the score is high, represented by those pinker lines in each column, in each row. The first syllable becomes flattened and shorter, while the second syllable rises and lessens. This is consistent with the right stress pattern we just mentioned, and when the score is low, it corresponds to the left stress pattern. And PC3 and PC2 mainly present individual speaker variation, but we still include these in the later classification in case there are any potential underlying patterns. And in the end, we compare both methods' performance on the test set. You can see the result in the confusion matrix. It shows that the k-means performed, I would say, poorly, especially in the recall rate for the right stressed patterns, which were frequently misclassified as left stressed. In contrast, the logistic regression model hit a 91.3% accuracy on the test set. Based on the classification result, we got the average curves for the two sandy patterns in each of the 16 tonal combinations, as you can see here in the right picture. These average curves were then used for speech synthesis to generate 32 dissyllabic word samples. And according to the evaluation from native speakers, the generated patterns felt highly natural and the stress was clearly identifiable. So to conclude, we have presented our automatic classification framework for Tensandi in Chinese dialects. It combines FPCA with mixed effect logistic regression. With our target adaptations, FPCA handles intersyllabic issues in internal languages effectively. It preserves the relative independence between syllables while systematically analyzing their covariance. Moreover, it also allows us to add covariance analysis of additional dimensional information, which is particularly meaningful for specific dialects. And though logistic regression is a supervised model, it has already significantly reduced the need for manual labeling, and so it achieve a solid classification occurrence. I think it's good enough for the linguistic research. So this frame can be extended to other dialects, even other languages or other research problems. But for future work, we plan to compare more classification models and hoping to get better results. And that's all my report. Thank you for your attention.
Okay, thank you. And let us give applause to Mr. Su.
Thank you.
Okay, is there any questions? No? Okay, so Ms. Su, I would like to pose you questions. First of all, so what motivated you to use two models from different approaches, that is supervised and unsupervised learning?
Thank you for your question. At the beginning, we just want to compare the supervised patterns and unsupervised models, which generally, which is better for our research. And k-means and the logistic regression, we just pick them from as a classic, the most classic method, I guess. Yes, it's kind of weird because they are very different, but the basic idea is just we want to compare the most general angle, that is unsupervised method better or supervised better. That's
Okay.
basically it. Like
Yes.
that.
Okay, when you decided to choose the k-means clustering, so how did you choose the number of the cluster?
Oh yeah, for the cluster, we do the elbow picture and some other estimate method, and we make it two, not only because it's the best result according to elbow plot, also because it's based on the language reality that in Wuhan, like the Shanghai patterns is clearly two patterns, like left stress and the right stress, as I mentioned before. So yes, the classic numbers is both the data and from the linguistic reality.
Oh, so basically, you decided to have two clusters instead of four tones for type of tones. Okay.
Yes.
Okay, I see. Okay, and when I saw that you presented the confusion metric, so it's like the raw data. Okay, so one small question. Raw data on confusion metric, but it's interesting because you highlighted the recall metric instead of precision, for example. So what is the reason behind that? Why you prefer recall instead of precision or accuracy in this case?
Yes, I present the accuracy too. But yes, I did not embrace that. The k-means, the accuracy of k-means clustering is 0.6, around 0.6, and the logistic regression is 0.9. Actually, according to this number, it's clearly which one is better. But we report the recall rate in specific because according to the results, the reason why k-means got such a low accuracy is because there is a very clear trend that it classified the right stress data to left stress very oftenly. So it's that's the main reason we think. So we report that again on the oral report. Yeah, that's the reason.
Okay, so thank you very much, Miss Su. So let us
Thank you.
give a big hand for Miss Su.
Thank you.
Okay, so I would like to check whether Mr. or Miss Ziatia Rafi is already joining the Zoom.
Yeah, I'm here. Am I
Ah,
audible?
Okay. Yes, yeah, you are audible enough. It's
Oh.
super. Good. So, Mr. Rafi will present on development of chatbot module in an intelligent tutoring system for English language learning using large language model. Mr. Rafi, time is yours.
Okay. Good afternoon, everyone. First of all, let me introduce myself. My name is Tia Rafi from Bandung Institute of Technology from Indonesia. Before I begin, I would like to sincerely apologize for not joining the conference on site or personal constraints. But I hope this presentation is still clear and still informative to all of you. Okay, today I'm going to present the development of chatbot module in an intelligent tutoring system for English language learning using large language model. This is a joint research with my supervisors. I would like to say thank you to my supervisors, Mrs. Ayu Purwarianti and also Mr. Samsu Sempena. Yeah, okay. And then, as the title suggests, we are going to focus on the chatbot module of the intelligent tutoring system. Okay, first of all, intelligent tutoring system, the background. English is the most widely spoken language with 1.4 billion speakers, according to the Ethnologue 2023. But unfortunately, in Indonesia, the English proficiency still ranks pretty low. It ranks 81st out of 111. This is according to Education First 2022. And this largely due to the shortages of the qualified teachers. And this issue gives opportunity to the intelligent tutoring system. Offers personalized learning, minimal teacher intervention. And also, will be very beneficial to address the issue of the lack qualified teachers. And also, the chatbot itself, leveraging the LLM, the modern chatbot leveraging LLM, gives context-aware tutoring, which is very beneficial for the self-learning. Okay, let's continue. And this is our methodologies. The first one is the data collections. Second one, after we get data, the base model comparison. Basically, we are comparing models, comparing prompts, which works the best and performs the best for base foundation to get the chatbot. And then after we found a single most performing models and prompts, we continue to the next experiment, which is model performance improvement. In this experiment, we are going to enhance our chatbot, our models performance, and also to develop into several use cases of the chatbot for the English language learning. And then after that, obviously, after the experiments concluded, we are going to give an evaluations to the models for the techniques we applied before. And then lastly, we are going to develop a chatbot module for the intelligent tutoring system. And that's our methodologies. And then let's continue for the prompts we are using for comparing the base models. Basically, we have 4 types of prompts, but it is divided into 2 languages, English and Indonesia. English means the prompts will be stated in English language, and Indonesia means the prompts will be stated in Indonesian language. Okay, for the first one is the simple task instructions. It contains a very simple prompt, a brief explanation of what is presented and what is the task to be completed. And then the second one, we have a gameplay. It contains a prompt of playing game related to a specific task. This is basically a gamification prompt based on White et al. 2023. It comes with 2 languages also, English and Indonesia. And then the continuation, we have a chain of thought. This is a classic chain of thought from Wei et al. This prompt is to activate complex reasoning abilities through intermediate steps. And then lastly, we have a tree of thoughts. This prompt allowed the model to correct its errors while gathering knowledge. This is from the Hulbert 2023. Yeah, basically we have these prompts and we also have these base models. Before selecting the models, we have a few criteria. The model have to be open source. You have to understand Indonesian and English context because we are going to develop this intelligent tutoring system for English learning for Indonesian students. And then the model have to have a moderate parameters. This is due to the limitation of the resources. And then the model should focus on the text generation model. We have these 5 models that we are going to compare. The first one is Gemma 7B Instruct to be exact. The parameter size is 7 billion. And then we have Llama 2 7B Chat. And then we have Merak 7B for version 4 model. And then we have Mistral. And then we also have Llama 3. All comes with a parameter size of 7 billion to 8 billion. And the quantization size of 4 bit. This is once again due to the computational limitation. And then for the model comparison experiment, for the dataset itself, by the time that we are doing the research, we face the challenges of getting the data we would like to have. So the dataset is synthetically generated using LLMs. It contains 40 English question answering test entries, and it's categorized into vocabulary, grammar, and also others. Others means reading, writing, passages, and so on. And then for the fields included in the datasets, there are inputs, basically just a question from student to the tutor, and the output, which is the tutor's answer to that questions. And for the inference parameters, we are following the previous experiment by Hick et al. 2023. The max token is 500, new token 1024, top P is 1, top K is 50, and the temperature is 0.3. And then for the metrics itself, we have these 3 metrics. Basically, we are going to have automated evaluations because there's a lot of combinations of model and prompts. So we have these 3, BERT F1 score, accuracy using G-eval, basically evaluation using a GPT 3.5 Turbo, and the informativeness also using G-eval. And all this in the F measures, so it's ranging from 0 to 1. And then for the result, as you can see here, Llama 3 with simple task instruction or the coded Llama 3 0N outperform other models with an average score of 0.8418. So you can see the score here. And after that, after we are getting the model and the prompt, we are going to use it as a base foundation to build our chatbot and go to the next step, which is model performance improvement. Okay, and this is the next experiment. We are going to implement a performance improvement to the model. The techniques we are using is the few-shot prompting. This is based on Brown et al. 2020, involved in providing models with several task demonstration during the inference. Basically, we are giving samples to the models of doing the task. And also for the chatbot, we would like to have a variety of use cases for the students and also for the tutors. So the chatbot can be used for student and can also be used by the tutor itself. For the students, there are student question answering. Basically, this is the use case we already implement previously in the model comparison. Basically, just a simple question and answering between students and the chatbots. And then the feedback generation is when the student, for example, answer a question incorrectly, and then the chatbot can give a feedback why they are wrong and so on. And then for the translation, this is simply a translation between Indonesia to English and vice versa. And also for the grammar correction, basically the input is a sentence, and then the model can correct the grammar. And for the tutor use case, there are tutor question answering. Basically, tutor can ask the chatbot anything in the context of English, for example, to ask about the curriculum, difficulty of the questions, and what method to teach the student and something like that. And then the question generation, tutors can use to generate questions, can provide some context if you want it to be multiple choices questions or short answer question or open-ended questions. And then for the answer generation, basically just giving answer, whether it is open-ended, closed-ended, or multiple choices. And for the explanation, generating explanations of a question given the question and also the answers. And we use 5 samples each for each few shot for each use cases. And then for the pre-prompts here, we are using the modified simple task instructions as the most performing prompts previously developed for all the use cases. As you can see here, we have a student question answering. This is the prompt and the tutor question answering. And also the prompt is like this, and the feedback generation, the translation is like this. Then this is for the grammar correction. You provided with a sentence, going to check the grammar of the questions, and for the question generation, you're going to be provided with context. You're going to generate an English lesson question and its correct answer. And I provided the format here so the model can write it correctly. And then this is for answer generation, also provided with an English question, you're going to generate an answer. And for the explanation, you're going to generate an explanation of the correct answer. Yeah, and then comes to the evaluations. We are going to compare few-shot model and the zero-shot model. For the inference parameters itself, we use the same as the previous experiment, but we increase the max length to 1000. This is due to we have a longer context, for example, generating passage or open-ended questions, something like that. And for the evaluation, we use 2 methods. We use a user-based evaluation and also automated evaluations. For the user-based evaluation, we use 5 annotators for this, and automated evaluation, we use geval with GPT-4 Turbo. And for the metrics we are using, we use the informativeness and accuracy. Basically, every response from the model, we are going to give it a score between 0 and 1 for all of the response, all of the combinations. And then here are the results for the manual evaluations. As you can see here, there are 4 columns. And for all of the use cases, the informativeness of the few shot, the informativeness of the zero shot, accuracy of the few shot, and the accuracy of the zero shot. And we also does the same for the geval for all of the metrics. And then in average, this is the result of the experiment. This is a few shot improvement. As we can see here, for the informativeness for the few shot model, we get 0.958, and zero shot one 0.73. So there's a 9.73 improvement. For the accuracy, for the few shot model, we see a 0.9649, and the shot for the 0.907, and we see 6.29% of improvement. And in average, 0.9614 for the few shot and 0.8903 for the zero shot. And hence the improvement average is around 7.97%. Yeah. And then after that, after we seen an improvement of the model, we develop a chatbot module. Not going to talk much about this. We develop backend applications leveraging some tech stacks such as Python with fast API with several functionalities. The first one is sending requests to the model. Obviously, we are going to take the response. And then the second one is storing and removing context of the chat. Basically, this is a create, read, update, and delete operations. And then, if I were to conclude this, from the experiment, Llama 3 8B Instruct was identified as the best performing models amongst other models for intelligent tutoring system chatbot using a simple task instruction prompt. And the second one, the performance enhancement using few shot techniques improved the base model by 7.97% with the informativeness score of 0.958 and the accuracy score of 0.9649. And lastly, the ITS chatbot module was successfully developed as a backend surface of applications. I think that's all from me. Thank you. Thank you very much for your attention.
Okay,
you.
thank you very much. And just give applause to Mr. Rafi. Yeah. Any questions? No? Okay, due to time limitation, I have one question only for you. So, if I'm not mistaken, you earlier said or described the task for the chatbot on the learner is like writing, reading, and so on. And so I would like to focus on writing. So how far is the writing skill of the student was given feedback by chatbot? I mean the feedback, what kind of feedback to give on the writing task?
Okay, so you're asking about how the student will benefit from the chatbot using the feedback generation use case, right?
Right.
And specifically for the writing. Yeah, for the writing, obviously, the questions will be an open-ended questions. For example, given main idea of the paragraph, and then the student is going to generate a text, a paragraph, or even the longer one, or even a story, something like that. And the feedback generation chatbot will check the correctness of the user's answers, the student's answers. For example, the grammar correctness checked, and also the thoroughness of the answers, and also the main idea, is it like everything's included in the response or not. But basically for the like close-ended questions or even a multiple choice questions, basically the model can just say that the answer is wrong. The correct answer is this because the blah, 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 blah. Yeah, I think that's the answer for me, if that's answered the questions.
Yes, okay. So I think it's enough, and thank you very much, Mr. Rafi. And this presentation concludes, ends the session, oral session 5 today. So please join me to give applause to all presenters. And I give time back to MC. Thank you.
Thank you very much to our 3 presenters on site, and also Ms. Wang Ping-su and Mr. Dia Ravi, who presented online. Thank you very much. Also to our session chair, Dr. Lucy. Please be seated. Thank you. Ladies and gentlemen, now we will come to the second and last poster sessions of this conference. There will be fabulous 11 group presenters who are excited to bring you into their amazing research displayed through the poster. So ladies and gentlemen, please kindly approach our presenters in the stair level of this auditorium. You may start to come to your posters to present. And here I'd like to preview the posters from the first one. The first poster created by Chan Sun Chen, Xiao Wen-chu, and Yuan Fulio, entitled Taiwanese Post-Tagging Without Training Data, an LLM model merging-based approach with Chinese resources. And the second one, the poster is created by Shoichi, Fier Kai, Pik Xiangsan, Yan Qiao, and Ai Chun Li, entitled Chinese Learners Processing of English Prosodic Boundaries, an ERP study. The third poster, created by Debolina Pramanik, Puja Bharati, Sabyasachi Chandra, Satya Prasad Gadamedi, Shyamal Kumar Desmanda, and Tarun Kanti Bhattacharya, entitled Native Language Identification in Multilingual Indian English Speech, a hybrid deep neural approach with feature space visualization. The next, the fourth poster created by Rikuto Yamanaka, Tsubasa Saito, Yuko Wakabayashi, and Norihide Kitaoka, entitled Speech Input Interface for Electronic Medical Record Supporting Automatic SOAP Generation Using Large Language Models. And the next, the fifth poster created by Ria Sil, Sabyasachi Chandra, and Pubali Maiti, entitled Advancements in Speaker Diarization, a comprehensive study integrating audio-visual, neural, and language model-based approaches. The sixth poster, created by Chu Young Ho and Wai Sam Lee, entitled Effects of Speech Rate and Syllable Position on the Temporal and Spectral Characteristics of Cantonese Vowels. And the seventh poster, created by Nathaniel Oko, entitled Oriental O-COCOSDA in the Philippines and Global Academic Landscape, Policy and Bibliometric Perspectives. The eighth poster, created by Jean-Roby Genitwen, Stephen Borja, Justin Eaton Ching, and Nathaniel Oko, entitled Case Studies on Error Checking for Tagalog and Bicol Language. And the ninth poster, created by Revano Fabiansyah Priyadi and Ari Ardianti Suryani, entitled Literature Review, Fusion and Attention Mechanism in Text and Image-Based Multimodal Sentiment Analysis. The 10th poster, created by Jean-Roby Genitwen, Stephen Borja, Erin Gabriel Chua, Gideon Chua, and Nathaniel Oko, entitled Integrating Semantic and Orthographic Features for Drug Name Similarity Analysis. And the last, the 11th poster, created by Wenyu Xia, Inten Weng, Xue Mei Hua, and Ping Teng, entitled The Influence of Emotional Prosody on Preschoolers' Perception of Mandarin Tones Under Noise, Benefits from Visual Articulatory Cues. This poster session will last for 1 hour until 3:30 p.m. So now, please have a wonderful exhibition. Presenters, you can come to your poster and welcoming the visitors to discuss and explain about your research. The time is yours.